Okay, this video is going to be over the limit comparison test. Target says students will apply the limit comparison test to a series using limits to infinity to determine the convergence of a series. So yesterday in class we left off with two series that looked very similar to a p-series but was not quite there because of the addition of a 5 or because of something else going on in the problem. So anytime we get a series that looks like but it's not quite, we tend to go to the limit comparison test. And that's what we're going to do today. This one's pretty simple, dealing with some fractions though. The limit comparison test says, suppose that we have two series, okay, where a sub n is the original series. We're going to label that one as our original. Let me get a pen here. That's going to be our original. And b sub n, that's going to be our comparison series, and that's going to make sense in a minute when we do a problem. Okay, both of these series do have to be positive. Most of our peer series, most of our series are, we haven't really gotten to negative series too much. It says if we take the limit as n approaches infinity of the ratio of those two series, so we're comparing them, if we get a value and it's finite and positive, then either both of the series will either diverge or converge. So the idea of getting a comparison series, we want to choose a series that we know that's pretty simple to prove divergence and convergence. So for example, if we look at 8, it says prove the convergence or divergence of each of the following series. So right here, if we think about it, that 1 and that n cubed represent our p series. But that 2 in front and that 5 is what's screwing it up. It's not making 100% p series, so I can't really use a p series test on it. But because it looks like it's almost a p-series, I can use that limit comparison test. So one thing we always want to do here is we want to always determine what we're going to compare it to. What we're going to do is we're going to take away all the fluff. So we're going to take away that 5 and we're going to take away that 2 and write a series without those two values. So I'm going to put, we want to compare it to. We always want to determine what series we're going to compare it to. So I'm going to compare it to 1 over n cubed. Like I said before, we're getting rid of the 2 in front, fluff. We're getting rid of that plus 5, fluff. Let me kind of write that one more time. Okay, so we're going to compare it to the series of that. Because we know that's a p-series, that p is greater or is equal to 3, which is greater than 1. So that p-series we already know is going to converge. So the next thing we want to do is take the limit of our comparison series and our original series. So these are the conditions. So as n approaches infinity, because these are infinite series, we'll look at our first series, our original series, and divide it by our comparison series. Okay, so we get a fraction divided by a fraction, which often we will in this case. So first thing we want to do is get rid of that situation and rewrite it as our first series times the reciprocal of our comparison series. And if we simplify that all the way down, we get the limit as n approaches infinity of n cubed over 2n cubed plus 5. And now we have a limit that we can actually take the value of. So I'm going to kind of go up a little bit. Okay, of course we're taking limits to infinity, so we're still going to use those three rules. If we look at our first term on top, let me get a different color. That term is our highest term on top, highest term on bottom. Because our exponents are the same, that means they're growing at the same rate, which means we are looking at our leading coefficient, so 1/2. Since that 1/2 is finite, it's a number, and it's positive, whatever 1 over n cubed does is what the other series is also going to do. So I need to first establish my comparison series. So the p-series. equals 3, which is greater than 1, converges by the p-series test. Okay, so we establish our comparison series, what our comparison series does. Therefore, I'm going to use my 3 dots. We want to write out the series we're actually proving. Remember I said there's quite a bit of writing in this unit because this doesn't have a proper name. And we have 2 series, we want to be very specific. And this one's also going to converge. But this one converges by limit comparison test. Okay, so here we're having to use 2 different tests. We're having to use the test for the comparison series and then the test for the overall series that we're dealing with, which is the limit comparison test. Okay, so we're having to use 2 different things here. Okay, so let's look at B. Okay, so if we think about it, remember when we take away all the fluff, any coefficients, any constant values, we really want to look at the highest term in numerator, highest term in denominator, and deal with that alone. So let's see what we're going to compare it to. Okay, we always want to tell our person what we're comparing it to. Okay, so we're going to take off the 4, we're going to take off the 3, and that leaves us with n to the 5th over n to the 6th. If we simplify that down, we actually get 1 over n, which I like that because that's our harmonic series, and we know that our harmonic series always diverges. So now I need to do my criteria or my conditions, which is that limit piece. So the first thing I'm going to do is set up my limit as n approaches infinity of my original series divided by my comparison series. Now I'm going to be dividing by 1 over n, so I'm just going to go straight into the multiplication of the reciprocal. I'm going to simplify that out really quickly. And we get n to the 6th over 3n to the 6th plus 4. And we look at our highest term on top, highest term on bottom, same power. So they're growing at the same speed, which means we're looking at the leading coefficients, which is 1/3. So there we go. So because that's finite and positive, whatever our comparison series does, so does our original series. So first I want to establish what my comparison series does. So because I compared it to the harmonic, I could say the harmonic series diverges. Okay, remember with harmonic, it always diverges, so just by saying harmonic, I can automatically say diverges. I don't really have to have a test. I can state the p-series test, but I don't have to for the harmonic series. So the harmonic series diverges, therefore, I'm going to use my 3 little dots, our original series, and I want to write out that series to be specific, leave no room for confusion. Also diverges by limit comparison. Okay, so what I want you to do, okay, so you've had 2 examples. So what I want you to do is look at the 2 examples at the bottom, and I'll help you with the comparison series, and then I want you to do the ratio and the limit, all of that, and come in tomorrow with an answer. Okay, so let's do the comparison series first. Okay. So this one, if we think about this n is really to the 3/2. Okay, so if we take away the 1, that fluff piece, we can compare to our series of 1 over n to the 3/2. Okay, so that's what we're going to compare it to. So finish out that problem. Okay, for this one, if we think about that right there, getting rid of that 1, we think of that 2n over 3n. That's geometric, okay, because they're both n is in the exponent alone. So we're going to compare it to a geometric. And we're going to put this as 1. Okay, so go ahead and try out those 2 problems at C and at D to determine convergence and divergence, and then of course write your statement. Come in tomorrow with any questions.